So if I have an electron and I throw it into hydrogen, so this diagram here is the hydrogen diagram with Schrodinger's equation taken into account, noting that that means there's different sublevels. So there's S, P, D, F, etc. That's what Schrodinger's equation tells us. But the other thing you notice is the S's are, the 1s is at one level, the 2s and 2p are exactly the same level, 3s, 3p, 3d, those are at the same level, 4s, 4p, 4d, 4f, those are at the same level. They're not drawn perfectly on here, but they should be all at the same energy level. This is energy along this axis, so increasing energy. So for hydrogen, if I throw an electron into a hydrogen atom, it's going to rattle its way down to the 1s level. All right, I'm going to draw an arrow saying that's my electron. Okay? So I've got one electron sitting down here in the bottom level. That's called the ground state. Now you remember we said we can put some energy in. We can send this guy up to a level here. And nature doesn't want to be there that long. It's going to drop down. So it's going to, if it goes down to this level, it's going to emit a certain color photon. If it goes to this level, it's going to emit a different photon. Why have I chosen blue compared to green? Blue is higher energy. How do I know it's higher energy? It's making a bigger drop. The bigger the drop, the higher the energy. Okay? So as these jump from one level down to a different, the energy gets greater and greater. We've already showed you how to calculate that. There's a formula we can use using the Rydberg equation to calculate the energy of the photon that actually comes out as it drops. Okay? But here's the important thing for this discussion. These energies are all at the same level for all the different suborbitals. So the Bohr model explained the energies in terms of these discrete energy levels, but Bohr didn't understand that hydrogen is the exception on the periodic table. Every other element follows a different set of rules. So he got one right but 99 wrong. Turns out all the rest of them, the energy levels are not exactly the same. They're slightly different. So the 1s is at a lower energy. That's the same. Then the next one we fill in is the 2s. So think of this as being like a concert, and you want to be right next to the stage. 1s are the closest ones, then 2s are the next one, then the 2p's are the next ones that we fill. Then the 3s are the next ones we fill, then the 3p's. Okay, so in terms of the periodic table, what happens is the 1s orbitals get filled first, then the 2s's, then the 2p's, then the 3s's, and if you notice on the periodic table, this level here is actually the principal quantum number. All right, that's pretty convenient. You just count down the number of rows. That tells you what the principal quantum number is. 3p is the next one. Everything's going great. 4s is the next one. Now we hit the first exception, transition metals. And if we look up here in the energy level, 4s gets filled next. We don't fill the 4p because it turns out 3d is actually a little bit lower in energy. So nature is going to want to start filling in the 3ds first. Okay, that's all these guys right here. Then the 4p's go next. Then the 5s's. Okay, 4p, 5s, 4d, 5p. All right, you see the pattern here? Now we're going to go to 6s. So basically the transition metals are one less, so it's basically n minus 1 is the transition metals. And then along comes these f orbitals, and they go right here. And notice they are actually n minus 2 in terms of what level they're on. Then the f's get filled, then we go d's, and then the p's. Okay, the whole structure of the periodic table then is based on this. Do you notice all the s's are grouped together? All the p's are grouped together. All the d's are grouped together. And then all the f's end up getting grouped together. Now look at really the f's would push this row down a bunch more, but it's easier to write the periodic table this way. So these get inserted over here. Let's go back to the prior figure, back to the periodic table here. All right, now I want you to note something. This is important. Do you notice, let's take oxygen. This has a configuration of 2s2, 2p4. Sulfur is 3s2, 3p4. Lithium, 2s1. Sodium, 3s1. Do you notice it's basically the same electron configuration when we jump down to the next row of the periodic table? In fact, if we can look down here, 2s2, 2p4, 3s2, 3p4, 4s2, 4p4, 5s2, 5p4. So, within a group in the periodic table, we have the same outer shell electron configuration. So the outer electrons are called valence electrons. These are super important. Valence electrons are where all the action is in chemistry. The bonding is because of valence electrons. Electrical properties. Does this conduct electricity or doesn't it conduct electricity? That's due to valence electrons. Optical properties are due to valence electrons. Does this transmit light? Doesn't it transmit light? Mechanical or magnetic properties. Is it magnetic? Is it not magnetic? Thermal properties due to valence electrons. So all the interesting stuff in materials comes from the valence electrons. So the outer electrons are called the valence electrons. The inner electrons are called core electrons. So you notice the way this figure is from your book, they don't include all the electrons. They're only including the valence electrons. So there's a shorthand way of writing the electron configuration. Let's take for lithium. We could write it this way, 1s2, 2s1. And for sodium, we could write 1s2, 2s2, 2p6, 3s1. You notice that figure only has the valence electrons. There's a shorthand way we could write this by noting that the prior element on the periodic table is a noble gas, and it has the configuration of the core electrons. So a shorthand way of writing lithium, now lithium's kind of short anyway, we could write, in brackets, we write it this way. We write the noble gas core, and then we write the valence electrons. So for sodium, we would say neon 3s1. All right, let's take silicon. That one, the prior one, is neon. And that is going to be, that's in the third row of the periodic table, so it's going to be 3s1, or excuse me, 3s2, 1, 2, 3p2 would be the electron configuration for silicon. Now you notice I'm kind of avoiding my examples I'm starting with. I'm avoiding the transition metals. Let's take one of the transition metals. Let's take vanadium. Okay, so vanadium is going to be, argon is the prior one, so it's going to be argon. And it's in the fourth period of the periodic table. 4s2, 1, 2, 3. 3d3 is my electron configuration for vanadium. All right, you notice what I did? Just count it over here. 1, 2, 3. So it's vanadium 3d3. And remember the d orbitals are n-1. The f orbitals are n-2. All right, let's take another one. Let's take tungsten, for example. Tungsten, symbol W. We got to go back to the prior one. That's xenon. And that is in the sixth row of the periodic table. So 6s2, you got to remember we got all these guys shoved in here. So we have to have 4f14, and then we have to have 1, 2, 3, 4. 5d4 is my electron configuration for tungsten. Okay. Now a couple things I want to note, and then I'm going to give you a couple exceptions. It wouldn't be chemistry without a few exceptions. All right, so one thing I want to note. Without counting how many boxes there are right here, how many elements there are, we can figure it out based on the type of orbitals that are being filled. These are f orbitals. F orbitals, let's see, L is equal to 0 is an S, 1 is a P, 2 is a D, 3 is an F. So L is equal to 3 for f orbitals. M sub L is equal to -3, -2, -1, 0, +1, +2, +3, 1, 2, 3, 4, 5, 6, 7 suborbitals. Each one can hold 2 electrons. Therefore, there are 14 boxes, 14 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's where that comes from. That's why those elements are like this. P orbitals. L is equal to 1. M sub L is equal to -1, 0, +1. There's 3 of them. Times 2. It means there's 6 possibilities. 1, 2, 3, 4, 5, 6. There's 2 s orbitals, and then this one there's 5 d orbitals. There must be 10 atoms going across. The entire periodic table is structured because of these quantum numbers, and because of these, specifically because of the m sub L values and the L values. Pretty cool, huh? All right, let's show you something else. Here's a point that I made a long time ago, and you probably don't remember it. I won't hold it against you. But I said hydrogen and helium are a little bit tricky. Remember I said we could make a pretty good case for putting helium right here on the periodic table. What would my pretty good case be for putting helium next to hydrogen on the left side of the periodic table? The pretty good case would be this is a 1s2, which is the same electron configuration as all these other guys, which are ns2. So from an electron configuration standpoint, we can make a very good argument for putting helium on the left side of the periodic table. That would keep all the s block elements together. However, I also said we could make a pretty good case for moving hydrogen into this space on the periodic table. Why would we do that? Well, hydrogen is a nonmetal. And these guys over here are all nonmetals. So you can make a good case from a nonmetal standpoint that the hydrogen should go over there. For whatever reason, it's been chosen to leave them like this, probably because it looks a little better symmetrically, but you could make a case for both of those being true. I think it's going to stay like this pretty much as long as we're around. The other reason why it makes sense to leave helium here is it is a noble gas. All these are noble gases, so chemically it's similar to all these guys. More similar to these than it is to the group 2 cations. Okay, we've learned about valence electrons. These are the valence electrons. We've learned about the core electrons, which is the noble gas core. We've learned how to write the electron configurations for the elements on the periodic table. Not so fast. We do have a few exceptions. If you look in here, this one has an exception, 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 these 3 guys have exceptions, that one has an exception, that one has an exception. All right, you see the pattern. And you notice where all the exceptions are coming from. They're all stinking transition metals. Okay, I don't want to have you worry about every exception in the transition metals, but I do want you to worry about these exceptions. Okay, these are called the coinage metals. Gold, silver, copper, and chromium is another exception. Let's talk about why those are exceptions, and you'll be able to pick these out and remember them. And it also explains why the other ones are too. Let's take a look at chromium first. All right, so chromium, the electron configuration for this is argon, and we would anticipate it to be 4s2, 1, 2, and then 3d, 1, 2, 3, 4, 3d4. All right, so if we're drawing boxes to stick electrons in, 4s2, 1, 2, 3, 4. That's what we would expect it to be. But it turns out in reality, it's really argon 4s1, 3d5. What happens is nature wants to put that extra one of those s electrons into the d orbital. Something like this. 2, 3, 4, 5. Oops, sorry. Not like that. Like that. Okay? Turns out this is more energetically stable. Nature likes to have shells that are all spin aligned with each other. It's a little bit more energetically stable to spin align a half-filled shell than it is to leave one box empty. Okay? Why is that? I don't know. That's the way nature has it. But it turns out it's more energetically favorable to either fill or half fill a shell. So this is the electron configuration for chromium. Let's take a look at copper. Copper has an argon core. We anticipate it to be 4s2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d9. That's what we anticipate the electron configuration to be. That should look something like this. 4s2, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, you notice what we have here. We've got a box that's got an empty hole in it. So once again, nature doesn't prefer that. Nature prefers this, 4s1, 3d10. Nature likes filled orbitals as well as half-filled orbitals. I did it again. Okay? And if you look at these configurations on here, you notice all three of those, gold, silver, copper, all have that configuration, 3d10. So it's filled the d orbitals up, very stable configuration. It looks like a noble gas actually, and there's just one extra electron in the s orbital. Okay? Nature prefers that. There's other exceptions on here. It's the same argument. It usually has to do with filling orbitals. I'm not going to have you know those. I do want you to know the coinage metals. I do want you to recognize that those are exceptions. And I do want you to know that chromium is one of the exceptions as well. Okay, so we have learned how to write the electron configurations for 90% of the elements on the periodic table, save for a couple of these funky ones in here. And just don't worry about them. I won't give you one of those on an exam. I can give you ones that follow the. I would give you ones that follow the rules, like over here, up here, or one of these four that are going to be one of the exceptions. But I'm not going to give you these other weird exceptions. Okay, and these guys, I'll give you any of those that follow the normal rules. So that'll take care of 90% of the elements on the periodic table.